Okay. Okay, I believe my audio is clear and shared screen is also visible to clearly everyone. So let's start our fifth tutorial of this course, Advanced Linear Algebra. So today is 21st February. Okay, so so let's start with some problems. So before that, I will just discuss some of the things which will be useful. That is, first is the transpose of a linear transformation. Okay, let V and W are two vector space over a field F. And recall that V star, that is dual, that is equals to all those linear functional from V to the field F such that f of C alpha plus beta is equals to C of F alpha plus F beta for all alpha beta coming from the vector space V and C is coming from the field F. This is called dual space space of all linear functional, space of all linear functionals. Okay, now similarly W star is equals to all those linear transformation from V to linear functionals from V to V such that G of C alpha dash plus beta dash is equals to C of G alpha dash plus G beta dash for all alpha dash beta dash coming from the vector space W and C is coming from the field F. Then let T be a linear transformation from V to W, be a linear transformation then this linear transformation induces this linear transformations induces another linear transformation T transpose, that is called from W star to V star. How it is defined? Defined by T transpose for any element G that is equals to G of G compose T. That is W star to V star is defined. So T transpose defined that sends any element to a new element T transpose G, which is a map from V to F, and T transpose G at any element alpha is equals to G of T alpha for all alpha belongs to the vector space V. Okay, this is called transpose of the linear. T transpose is a linear transformation called transpose. This linear transformation, that is T transpose, is called a transpose of the linear transformation T. Okay, now this is one can easily visualize how one can visualize. So let's take V is the vector space and W is the, just let me write it here. So let V is the vector space, W is the another vector space, and T be the linear transformation from V to W. Now all linear functionals are actually mapped, from V to F, and similarly linear transformation on W are mapped. So these are the element. Okay, these are the element. So now for example, if a map is G is here, suppose G is the map here, so T transpose is the map here. This is the T transpose. So T transpose actually, this will map T transpose, actually this is belongs to W star and this belongs to V star. So basically this diagram commutes. Now one can write like this way: T transpose is defined in such a way, T transpose defined in such a way such that this diagram commutes. Okay, so this is the linear transformation, this is the transpose of the linear transformations. Okay, now we know that if V and W are finite dimensional vector space over a same field F with dimension of V is equals to n and dimension of W is equals to m, then for a fixed order basis, for a pair of fixed order basis, of V and W, one can represent T by n, m by n matrix with entries from the field F. Okay, also for a fixed order basis, for a fixed pair of order basis of V and W, pair of ordered basis of V and W, there exists one correspondence between set of or space of between LVW, that is space of all linear transformations, and m by n with field entry, space of all m by n matrix with entries from F. Okay, so these two things are already there, but now main important fact is that we know that there exist, we know that for a given order basis of V, for a given order, okay, let's write on some other dimension, we know that dimension of V is equals to dimension of V star, that is dual. And for a fixed ordered basis of V, there exists a ordered basis, fixed ordered basis. Let's write that ordered basis like this way, or like alpha 1, alpha 2, alpha n of V. There exists an ordered basis f1 dot fn of V star such that fi alpha j is equals to delta ij, that is equals to 1 if I equals to j, or 0 if I not equals to j, right? Now similarly we have the same thing. Similarly, the similar thing happens with V. Similar things happens for W, right? Now let A belongs to M by n order matrix over the field F. B the matrix representation of T with respect to a fixed pair with respect to a fixed pair of ordered basis of V and W. Okay, so now a natural question, so one can ask, does there exist any relation between matrix representation of T and T transpose? The answer is yes. What is that? Then matrix representation of T, matrix representation of the T transpose of T is matrix representation of T transpose with respect to the corresponding dual basis. With respect to the corresponding ordered basis of W star V star, so the corresponding order basis W star of V star, that is dual basis, is A transpose, usual matrix transpose. So what is it is saying? It is saying let T from V to W and let beta and beta dash are order basis of V and W respectively. Okay, of V and W respectively, and beta dash, let's write it is as transpose, and beta dash transpose are corresponding dual basis of V star and W star, okay, respectively. if t with respect to order basis beta beta dash is equals to matrix A, that is constrained in m by n order matrix over the field A, then T transpose, that is a map from W star to V star, then the matrix representation will be contained in n by m matrix over the field F, and T transpose with respect to order basis beta star is equals to A transpose. Okay, so this is the thing. Now this is one fact, and second fact is that similarity of matrix. Consider matrix representation of linear operator, one correspondence. Okay, now we know if A be the m by n matrix over a field F, be the matrix okay, so basically I just want to write it. Let T from V to V be a linear operator on a finite dimensional vector space V with dimension of V is actually n, right? And let A belongs to this is n by n matrix, coming from the field A, be the matrix representation of T with respect to a ordered basis. Now we know if we change the order basis of V, then matrix representation will change. And new matrix representation of T with changed order basis is given by P transpose AP for some invertible n by n matrix. Okay, so that is T with respect to beta dash is equals to T with respect to beta and P, right? And for any matrix it is known that let A be an m by n matrix over the field F, then a matrix B belongs to the this is not n by n, this is I am taking as n by n, then n by n over the field F is called similar to A if B is equals to P inverse AP for some invertible matrix P in n by n order matrix. Okay, so this is the thing. So that is, therefore Therefore matrices corresponding to different order bases are similar. Corresponding to different, so matrices of a linear transformation on a finite dimensional vector space V, matrices of a linear operator corresponding to an order base linear operator on a finite dimensional vector space are similar corresponding to a different order basis similar. Okay, just 1 minute. So therefore now we'll start some problems. So let's start some problems. So what is this problem? This is problem number 10. So this is problem number 1. So where it is given. So let V be a vector space of all polynomials over R and F be the linear functional defined by f of p. So f be the linear functional, from the vector space. So let's write V is equals to space of all polynomials over R, and f from V to R be a linear functional, given by f at any polynomial p is equals to 1, 2, 3 px dx. Okay, let d be the differential operator. Let d from V to V be the differential operator, that is d of any polynomial p is equals to p dashed. Okay, so now question is that then what is dt fp? So this is what it is asked. Now when let px equals to 1 minus x plus 3x square be a fixed polynomial, be a fixed polynomial, if I'm not correct, yeah, be a fixed polynomial, then what is d transpose f at the point p? This is asked. So now we know that d transpose is the transpose of the linear operator of the operator d, then d transpose of an element f at the point P is equals to P of dP, right? So now it is known that for P, when P is equals to this, when Px is equals to 1 minus x plus 3x square, then d of P, that is at the point x, that is differentiation, so derivative will be minus 1 plus 6x. So then this will be f of minus 1 plus 6x, that is equals to integration 1 to 3 minus 1 plus 6x whole dx, that is equals to minus x plus 3x square 1 to 3, that is equals to will be minus 3 plus 27 minus 1 plus 3, that is equals to 24 minus 2, that is equals to 22. So which option is correct? This option is correct. So all other option automatically false. So option B is correct. B is correct. So let's do the next questions. So what next questions? This is 3. So next questions. So this is just, for example, this is the next questions. What it says is that so next question says that let V be a vector space. Let V be a space of all n by matrices over the field. Just 1 second. Let V be the space of all n by n matrices with over the field F, and T be a linear transformation on V such that TA equals to BA minus AB for a fixed matrix B. And then T transpose denotes the transpose of T, and let F be the function on V defined by F equals to trace of A. So so let then T transpose of F, it is asked to define. Okay, what will be the T transpose of A? T transpose of A. Okay, let V be the, here it is says that V be the space of all n by n matrices over the field F, that is space of all n by n over F. Okay, be the space of all n by matrices over the field A, and let T be the linear transformation T from V to V defined by T of A is equals to BA minus AB for a fixed matrix B in n by n. Okay, now it is known that for a matrix A is equals to Aij in n by n, trace of A is actually, that is trace of A, that is equals to, or one can write full form, trace of A, that is equals to summation of Aii, that means sum of all diagonal entries, right? That is diagonal entries. Okay. So sum of all diagonal entries. Okay, so now what is the question here? It is asked, so T transpose, so let T be the linear transformation, T be the linear transformation. So T is fixed vector for a, now then T is defined by T of a matrix A is equals to T of a matrix A is equals to trace of the matrix A, right? Then here it is asked to find the trace of Fa, right, where Fa is equals to this. Let Fa be a functional. Let F from V to R, no sorry, let T be a linear transformation, sorry, T is defined, let F be a linear transformation. Let F from V to R be a linear functional given by F of A is equals to trace of A. Then by definition, T transpose of F at A is equals to F of T, right? That is equals to trace of AB minus B. Okay, for all, her B is a fixed matrix, for all A belongs to the matrix n by n. Okay, so now what it is asked is that let V be n by n matrix, T be an intersection from V to B. Let T denote the transpose of T and A be the linear function of A defined by trace of A. And what is trace of Fm? Okay, so now let's calculate what is trace of A. Trace of AB minus BA is equals to trace of AB minus trace of BA. Okay, this is equals to one can write summation of I equals to 1 to n, summation of k equals to 1 to n aik bik, okay, minus summation of I equals to, or I can change it to new index, j equals to 1 to n, summation of k equals to 1 to n b jk a kj. Okay, this can be written. So I will fix the first one and change the second expression. So this will be k equals to 1 to n aik bik minus, I will change the sum. This sum can be changed easily because here total sum is of finite number of terms. Okay, so this can be written as summation j equals to 1 to n b jk a kj, right? One can write this way. Now this can be written as I equals to 1 to n summation of k equals to 1 to n aik bik minus summation of k equals to 1 to n, this can be written as j equals to 1 to n kj bjk. Okay, so now these two sum are same, then this is 0. Okay, so therefore, okay, these two sum are same, so therefore this will be 0. Okay, so now, so therefore only correct option is this one, so all other option automatically wrong. Okay, so let's do the questions number 3. Okay, so now we'll do the another questions that okay, so this will do. So So this is the question number, another questions. So what it says, let T be a linear transformation, linear operator on R3 which is represented in the standard order basis. So for R3 the standard order basis is, so standard ordered basis is 1 0 0 0 1 0 0 0 1. Okay, so standard order basis by the now T be a linear transformation from R3 to R3, T be a linear transformation from R3 to R3. Let's take it as beta. Okay, be linear transformation, linear operator, then T with respect to this standard order basis is given by this matrix 1 2 1 6 minus 1 0 minus 1 minus 2 minus 1. Okay, now the characteristics values of T it is asked to find. So let's do something for characteristics values. Okay, so for that we will just some given the what is called characteristics value. Okay, or one can do one more thing. Okay, let's try whether this is available or not. Okay, so let's keep it here. Okay, so we'll do what is characteristics value first. Okay, characteristics values or eigenvalues. Let T from V to V be a linear operator. Okay, on a linear operator on a vector space V over F. Okay, then a scalar lambda belongs to F is called a characteristics value or eigenvalue if there exists a vector alpha belongs to V such that alpha is not equals to 0, such that T of alpha is equals to lambda alpha. Okay, so when V is a finite dimensional vector space, then for ordered basis beta, T with respect to B beta dash is equals to is n of dimension n, then is a matrix of order n by n. Okay, order n by n. Okay, so in that case, so then lambda belongs to F is an eigenvalue if and only T beta dash minus lambda I as a matrix is singular or not invertible. Okay, okay, so that is equivalent to the fact that determinant of this matrix minus lambda I is equals to 0. Okay, now being an n by n matrix over f over a field f, determinant of t b dash b dash minus lambda I is a polynomial of degree n. This polynomial is called polynomial of degree n. Okay, now so as we have seen, if we change order basis of t, order basis of the vector space V, then the matrix representation, matrix of T will change to a new matrix of the form P inverse T B B dash so there is no beta dash here because we are considering a single order basis here. So this will be T beta dash T. Okay, and it is clear that determinant of P minus TB P minus lambda I is equals to determinant of TB minus lambda I. Okay, this is easy check. Okay, now therefore the matrix, therefore this polynomial of degree n does not depend on the choice of order basis of V. This polynomial is called characteristics polynomial. Characteristics polynomial of T. Note that all these things are happening only for the fact that whenever the V is a finite dimensional vector space. Okay, in that situation all these things are happening, because when V is not finite dimensional vector space, in that case we don't know whether the matrix representation is there is a finite, whether we don't know not we actually, in that case matrix will not be a finite order matrix. Okay, so this polynomial is called characteristics polynomial. Okay, now recall that that there exists a vector alpha not equals to 0 in V such that T of alpha is equals to lambda alpha if and only determinant of TB minus lambda I is equals to 0. Okay, so that is for any arbitrary ordered basis of B. Okay, that is lambda is an characteristics value or eigenvalue if and only lambda is a solution of the characteristics polynomial, solution of the characteristics polynomial determinant of TB minus lambda, or I can write here x because here I am writing lambda is equals to 0. So this polynomial, so solution or root of a solution, there will not be solution, so root of the characteristics polynomial root of the characteristic polynomial this. So therefore and therefore all the roots, therefore if there exists a lambda, if lambda belongs to f such that determinant of tb minus xi is equals to 0, lambda is equals to 0, then lambda is an characteristic value, then lambda is an characteristics value. So therefore what is happening here, actually let's take T is a linear operator from a finite dimensional vector space V to V. T has a linear matrix representation. So with respect to any order basis, consider determinant of Tb minus lambda is equals to 0. That will be an n degree polynomial, that is called characteristic polynomial. So roots of that characteristic polynomial is actually the eigenvalues of a linear operator. Similarly, if lambda is an eigenvalue, then that should satisfy this condition. So here what is happening in these questions, this Tb is a linear operator. So Tb is given by this way. So now it is asked to find what are the characteristics values of T. So therefore the lambda will be an characteristics value if and only, therefore lambda is an characteristics value. So here lambda is in field, lambda is in R. Lambda is an characteristic value if and only Tb minus lambda I, determinant of this is equals to 0, or if and only, or 1 minus lambda 2 1 6 minus 1 minus lambda 0 minus 1 minus 2 minus 1 minus lambda, determinant of this or this matrix is equals to 0. That is, so usual determinant, that is 1 minus lambda 1 plus lambda square minus 2, this will be minus 6 lambda, this is 0, plus 1 minus 2 minus 1 minus lambda, this is the case. So that is lambda plus 1 square 1 minus lambda minus 12 plus 6 lambda. So let's break it. So this will be 1 plus lambda into 1 minus lambda square plus 12 lambda minus 11 minus 13 and it will be minus lambda is equals to 0. That is saying that 1 minus lambda square plus lambda minus lambda cube plus 11 lambda minus 1 is equals to 0. So 1 cancel out. Therefore what we are having, actually we are having that lambda cube plus lambda square minus 12 lambda equals to 0. So in this case lambda will be, so one can easily take solution common, that lambda square plus lambda minus 12 equals to 0. So therefore it will be lambda 4 lambda minus 3 is equals to 0. So therefore lambda is equals to 0, 3 or minus 4. So these are all eigenvalues of T, right? Because that does not depend on the matrix. So therefore what are the option is correct? So here option is correct is the 0, 3 minus 4. So 0, 3 minus 4, this is correct option, all other option is false. Okay, so this is question 3. So therefore one can write option C is correct. Okay, option C is correct. Now we are going to discuss another problem, that is problem number 4. This is problem number 4. What it says is that, okay, so what it says, let M2R denote the 2 by 2 real matrix and let A belongs to be of trace 2 and determinant minus 3. Consider the linear transformation T from M2R defined by this way. So here V is the vector space, that is taken as M2R be the space of all space of all 2 by 2 order real matrix, 2 by 2 order matrices, and let A be a matrix of the order M2R with for which trace of A is equals to 2 and determinant of A is equals to -3. Okay, consider the linear transformation T from M2R to M2R defined by TB equals to AB. So as determinant is non-zero, so A is invertible matrix. A is invertible matrix. So here I am just want to let A be an n by n matrix over a field F that we can take what I want to that we can take complex over a field A where F is equals to either complex or real, whatever it is. Then determinant of A minus lambda I, that will be, there is an interesting pattern. That pattern is says that will be lambda to the power n minus trace of the matrix A lambda to the power n minus 1 plus all the entries, then minus 1 whole to the power n determinant of A. So in particular also I just want to add some things also. If lambda 1 lambda 2 lambda n with eigenvalue values of A with repetition, that means if there is a eigenvalue corresponding, I mean if an eigenvalue is repeating in the characteristics polynomial, then still we are counting that with repetition. Then trace of the matrix A is equals to summation of lambda I equals to 1 to n, and the determinant of the matrix A, that is equals to product of lambda I equals to 1 to n. So therefore if, I mean in any way you can go ahead, either if A is a matrix, so you can go in any way. In particular, if trace of A is equals to 2 and the determinant of A is equals to -3 for a matrix A in the real matrix, 2 by 2 order on the field real number, so in that case, then if lambda is an eigenvalue, then lambda 1 plus lambda 2, if lambda 1 lambda 2, this is the possible maximum possible eigenvalues is, then because characteristics polynomial of a n by n matrix is of degree n, so the maximum possible roots of that polynomial is n, so therefore maximum possible number of eigenvalues of an n by n matrix is maximum possible distinct eigenvalues of an n by n matrix is n. So therefore here as the matrix is of order 2, so let's lambda 1 lambda 2 are the two possible eigenvalues that they can repeat, I mean lambda 1 can be equals to lambda 2. So then what we are getting here, according to the previous thing, then we are getting two way one can look at, then lambda 1 plus lambda 2 is equals to 2, and lambda 1 lambda 2, that is equals to determinant, that is equals to -3. So one can solve this one, or characteristics polynomial of A is given by lambda square minus 2 lambda minus 3 is equals to 0. So therefore here will be lambda minus 3 and lambda plus 1 equals to 0. Therefore lambda equals to minus 1 3. These two are the eigenvalue. So here is the diagonalization concept. So let's go ahead for diagonalization. So for diagonalization we'll recall something that is called diagonalizable linear operator or matrix, whatever. Let V be a finite dimensional vector space, and T from V to V be a dimension of V is take n linear operator. Then T is said to be okay. So before doing all these things, I'll just tell you what is eigenvector. As you recall that, or we can write here also, and alpha is called eigenvector corresponding eigenvalue lambda. Okay, eigenvector of T, okay, corresponding to lambda. So therefore we can keep it whatever we are writing, that is, let V be a finite dimensional vector space over a field F with dimension of V is equals to n. Let T from V to V be a linear operator, then T is said to be diagonalizable if and only if there exists an ordered basis of V consisting eigenvectors of T. So let V be a finite dimensional vector space and T be a linear operator from a vector space V to V. That is actually to define the diagonalizable, we don't need finite dimensional, but for a matrix we need. That I will discuss, but for example you can assume finite dimensional. But finite dimensional is not necessary to define a diagonalizable operator. Okay, then linear operator, then T is said to be diagonalizable if and only if there exists an ordered basis, as said to be writing. So it will be only if there exists an ordered basis of V consisting eigenvectors of T. Okay, so and that is equivalent to equivalently n by n matrix A belongs to n by n matrix space is said to be diagonalizable, if and only there exists an invertible order, invertible matrix P on this space such that P inverse AP is diagonal. So these two factors equal. These two facts are equivalent, not equal, equivalent. Okay, what is the fact is that let's take V is a finite dimensional vector space, and let's take alpha 1, alpha 2, alpha n is an order basis consisting eigenvalue, ordered basis consisting eigenvectors. Okay, consisting eigenvectors. Then T of alpha I is equals to will be lambda I alpha I for some eigen value lambda I. So then matrix representation of T, therefore matrix representation of T with respect to this ordered basis is this diagonal matrix lambda 1 all the way lambda I. Okay, all other integers 0, lambda 1, lambda 2, lambda. They lambda I can be repeat. Okay, but what we have till now we have discussed is that the matrix representation of a linear operator on a finite dimensional vector space that will change by to a similar matrix if we change the order basis. So for example, if let's consider T is a linear operator from a vector space V to B, and B with respect to a fixed order basis B, T has a matrix A. Now it is saying that there exists an order basis consisting eigenvectors. So order basis consisting eigenvectors. So in that case, the basis change matrix P, suppose beta dash is the order basis consisting eigenvector. So there must be P is a matrix of order n by n which is invertible and which is the basis change matrix. So in that case, the matrix representation of T beta dash will be T inverse TB T inverse P inverse TB P. So that means this will be diagonal. So that means P inverse AP is diagonal. So this is these two factors similar. And conversely, if we have a matrix P which is invertible for which PAP is diagonalizable, so in that case one can choose a basis beta dash of the vector space V, order basis beta dash of the vector space V, for which the matrix of T will be diagonal. Okay, that is TP inverse AP, right? So that means that is saying that all the entries of beta dash are actually eigenvector of the linear transformation T on the vector space V. So therefore these two factor equivalent. So this is the diagonalizable, as this is the diagonalizable. But there is some interesting fact. Let Px be the characteristics polynomial, and let Px is equals to x minus lambda 1 to the power n1 all the way x minus lambda k to the power nk. So as we know that characteristics polynomial is of degree n, so this will be n, right? This will be n, and each of lambda 1, lambda k are distinct eigenvalue of of T. Okay, or a matrix be a characteristic polynomial of a linear transformation of a matrix A or a linear transformation, because this is valid, or a linear operator, then okay, let me write it clearly, be a polynomial of my matrix A or a linear operator. Okay, so in that case, because what I was saying that for a linear operator on a finite dimensional vector space, so in that case on a vector space of dimension 2, on a vector space of dimension n. Okay, so in that case so in that case characteristics polynomial will be this way, and n will be the maximum degree. So these are the distinct eigenvalues. Okay, so now we have seen that, recall that alpha vector space V is a eigenvector corresponding to is a eigenvector is an corresponding to a eigenvalue or characteristics value, same thing. Value lambda I if t of alpha is equals to lambda I alpha, right? So but alpha should be not equals to 0. Recall that alpha not equals to 0, that is, so then eigenvectors are actually, therefore eigenvectors are actually solution of the equation t minus lambda I alpha is equals to 0. But here we are considering alpha is non-zero. So in that case, if we consider extra that alpha is 0 also included, so in that case, then so therefore the set alpha belongs to V such that t minus lambda I alpha is equals to 0 is called, so here that we are not considering alpha is not equals to 0, that we are not considering, that means 0 is included here, that is called eigenspace corresponding to eigenspace corresponding to the eigenvalue lambda I. Okay, so let okay, let's take this is di dk, so this will be d1 plus d2 all the way dk is equals to n. So let ni is equals to dimension of this space, this will form a vector space. Okay, check, this will form a vector space, check, this is a subspace of V. Okay, so so now clearly it is known that ni is less than equals to di for all I equals to 1 to d. Why this is true? Okay, that I will not discuss it because that will take long time. Okay, so therefore a theorem says that T is a linear operator T, linear operator T on a finite dimensional vector space V on a finite dimensional vector space V of dimension n or a matrix, n by matrix of order n. So let linear transformation T is diagonalizable if and only this ni is equals to di, that is the number of repetition of eigenvalue that is number of repetition of eigenvalues in the characteristics polynomial is same with the dimension of the null space, dimension of the eigenspace corresponding to that eigenvalue. Corresponding to eigenvalue. Okay, so this is the thing. So therefore let's get back to the back to the problem. Okay, so let's back to the problem. What was problem? I'll just write the matrix here because that was, so here it is said that let A be the matrix of with trace 2 and determinant 3. So T B is the this one. So these are the option. 2 is eigenvalue of 2. T is not an invertible. T B equals to B for some equals to, and T is diagonalizable. Okay, all these things are there. Okay. So I'll just recall something, and we have obtained that the eigenvalues of T are actually, here minus 1 and 3. Recall that for the matrix A, recall that the eigenvalues of the matrix A belongs to M2 are minus 1 and 3. Okay, so therefore A is diagonalizable as all the eigenvalues are distinct. All the eigenvalues are distinct, then A is diagonalizable. That is, there exists an invertible matrix P in this matrices of order 2 by 2 such that P inverse AP is diagonal. Okay, so therefore this is diagonal. Okay, so therefore is diagonal. Okay, what is one fact we are sharing here? If we have all the eigenvalues of a linear operator of a matrix or a matrix are distinct, so in that case diagonalizable, because in this case by default Ni is equals to Di, right? So as we have distinct eigenvalue, so corresponding to each eigenvalue the repetition is once. Okay, so as here Di is equals to 1. Okay, but Ni is the eigenvector corresponding to each eigenvalue. Now whenever, suppose we have a eigenvalue, okay, and that is repeating once, so in that case if we so there must exist a non-zero vector, right? So that means the dimension of the eigenspace that will also be 1. So therefore this Ni equals to Di. So in that case this is diagonalizable. Okay, Okay, so this is the reason that all the matrices are diagonalizable. Okay, sorry, with a matrix which has distinct eigenvalue, that is diagonalizable. So in this case A is diagonalizable, and the matrix T, let T be a linear operator. T be a linear operator from the space of all matrix of order 2 by 2 defined by T of A is equals to AB minus BA. I think that was the AB, only AB. TAB equals to AB. A is the fixed AB. Sorry, I am writing something wrong. A is the matrix. TB equals to AB. Okay, TB equals to AB. That is left multiplication. Okay, TB is equals to AB for a matrix. A is in the M2. Okay, so this is the for any matrix for any matrix B in M2. Okay, so let E11 that is equals to 1 0 0 0, E12 that is, okay, let's take E21, E21 that is equals to 0 1 0 0, E12 that is equals to 0 1 0 0, and E22 that is equals to 0 0 0 1. Then this set E11, E21, E12 and E22 forms an ordered basis of the space M2R. Okay, now with that ordered basis the matrix, then with this let A is equals to A11, A12, A21, A22, that is a fixed matrix. Then with this ordered basis let A equals to this, that is the matrix in M2R, for which we have two eigenvalue -1 and 3, but that will be used later. Okay, with this order basis, T of E11 that will be left multiplication by A. Okay, so that will be A11, A12, A21, A22. So that with the matrix 1 0 0 0, that will be this will be A11. Okay, now this will be 0, A21 0. So therefore what we are getting, A11 E11 plus A21 E21. Okay, and similarly T of E, similarly what we'll get, T of E21 that is equals to will be A12 E11 plus A22 E21. Okay, and T of E12 that is equals to A11 E12 plus A21 E22, and T of E22 that is equals to A12 E12 plus A22 E22, right? So then matrix of T is given by, so let's take, this is the order basis, then beta is equals to, this is the order basis, then matrix of T is given by T with respect to matrix, that will be A11 A12 A21 A22 0 0 0 0 0 0 0 0 A11 A12 A21 A22. Now recall that A11 A12 A21 A22 is equals to A is diagonalizable. And P inverse AP is diagonal matrix for an invertible matrix P. Okay, P. Then consider P dash is equals to P0 0 P is inside that M4 of the real number R, that is 4 by 4 matrix. Then it is clear that P inverse TBP is equals to, this will be P inverse AP 0 0 P inverse AP is diagonal. Therefore T is diagonalizable. So this is one option, so that is saying that option D is correct. But note that -1 and 3 are eigen values of A. Then as matrix representation of T is equals to something like A0 0, A, here each of these 0 are also of order 2 by 2. Then eigenvalues of T are -1 3 with repetition twice each, so that means each eigenvalue is repeating twice. So these are the all eigenvalues. So as none of the eigenvalue is 0, as none of the eigenvalue of T is 0, then T is invertible. Okay, so now let's get back to the options. So T is diagonalizable, that we have seen. 2 is an eigenvalue, that is false because -1 and 3 are the only eigenvalues. T is not invertible, that is also false because none of the eigenvalues are 0, so therefore T is invertible. And third option, that TB equals to B for some B not equals to 0, and this will happen only when 1 is the eigenvalue, but eigenvalue 1 is not an eigenvalue, -1 is an eigenvalue, so therefore this option is also incorrect. So let's go to the next problem. Okay, so next problem, what it is? Okay, this is done. Okay, so this is the next problem. So what it says, that let A be a 3 by 3 matrix with real entries. Which of the following statement is or are correct? Okay, this is the question. Okay, so here before answering the question, I'll say one thing, that I'll just check. But what are the options? Let's check. A is necessarily diagonalizable. If A has distinct real eigenvalues, then it is diagonalizable over R. Okay, if A has distinct eigenvalues, then it is diagonalizable over C. Okay, if all eigenvalues of A are non-zero, then it is diagonalizable over R. So these two options are correct, because as we have recall that recall that if all the eigenvalues, if A has distinct real eigenvalues, then it is a diagonalizable over R. Okay, if A has distinct real eigenvalues, then it is diagonalizable. Okay, so just a minute. Okay, so here clear that if A has distinct eigenvalues, then it is diagonalizable over C. That's true, that we have shown. Okay, that I am just recall, if all the eigenvalues are distinct, then it is diagonalizable. Okay, so this option is correct. So this is, so therefore this is also true because A has distinct real eigenvalues. Okay, all the eigenvalues are real and distinct. So in that case, all the eigenvalues are real and distinct. Eigenvalues are real and distinct. So in that case, this is true. So if A has distinct eigenvalues, then it is diagonalizable over R. So therefore, okay, so these two are correct. If all eigenvalues are non-zero, then it is diagonalizable over C. That is false, because let A is equals to 0 1 0 0, right? So in that case, A is okay, non-zero. It is asked to have non-zero. 1 1. So here A is, only eigenvalue of A is eigenvalue of A is 1. So in that case, A is, but A is, in this case, but A is not diagonalizable. But A is not diagonalizable. Okay, why A is not diagonalizable? Because characteristics, I mean, how one can show that it is not diagonalizable. So only eigenvalue is 1. So why this is true? Because let's take x1 x2 transpose, that is belongs to real 2, is an eigenvector corresponding to the eigenvalue 1. So then 1 1 0 1, that is with respect to x1 x2 is equals to, supposed to be x1 x2. But what is the left hand side? Left hand side says that x1 plus x2, and right hand side is that x2. This is equals to x1 x2. So that implies that x1 plus x2 is equals to x1 and x2 is equals to x2. That implies that x1 x2 is equals to 0. Okay, so but no information about x1. So therefore 0 comma 1 x1 can be, therefore c comma 0 such that c belongs to real are only possible eigenvalue, are only possible eigenvectors, so C is not equal to 0, eigenvectors of A, and no other eigenvector is there, no other possible eigenvector is there. So this is the only possible eigenvector. So that and this space and this has dimension and this eigenspace of 1. So therefore dimension of the eigenspace of 1, dimension of the eigenspace of 1 is 1. Okay, eigenspace is 1. Okay, eigenspace is 1. So there is not possible to have a basis consisting all eigenvectors for which the matrix, there is not possible to have a eigen basis consisting all eigenvectors, because there is only possible one eigenvector is there, that is, so that has dimension 1, but here we must have dimension 2 for space of all eigenvectors, but here it is not the case. So therefore it is not possible to have a ordered basis consisting all eigenvectors. Consequently A is not diagonalizable. Okay, so that's why it is not diagonalizable, and then A is necessarily diagonalizable over, that is also false coming from here. If all eigenvalues are non-zero, then okay, let's so okay, so recall that if all the eigenvalues over are distinct over the field C, that is very important. Okay, distinct, then it is diagonalizable. Then the matrix A is diagonalizable. So that says option C is correct. Okay, now let A is equals to this, so this matrix is not diagonalizable. So first option, that A is necessarily diagonalizable, that is false. Second option, if all the eigenvalues were non-zero, then it is diagonalizable, that is also false, because here all the eigenvalues, here is only one eigenvalue, that is 1, so and that is non-zero. So this gives that therefore option A and D are false. Okay, now for option B, what it says, if it has all distinct eigenvalues, all distinct real eigenvalues, then if it has distinct real eigenvalue, if A has distinct real eigenvalues, then it is diagonalizable. This is very interesting. Let's look at it, because this is not direct. Okay, so let's remove this one. This is not that direct. Okay, maybe you can correct without just only guessing, but why this is true, that is what I'm just trying to say. Let's if okay, these two options are incorrect, that is clear. So this, if A has distinct eigenvalues over the complex field C, because this is algebraically closed, so any matrix can be decomposed and all the possible eigenvalues will be there, but real number is interesting. Okay, option B, so that is says that all if A has distinct eigenvalues, if A has distinct real eigenvalues, then A is diagonalizable. Okay, so that is says that all if A has distinct eigenvalues, if A has distinct real eigenvalues, then A is diagonalizable. Then A is not diagonalizable, that is false. Okay, then A is diagonalizable over R. This is the option B. Okay, so I just want to consider, let's take an X matrix 0 1 minus 1 0. Let A is equals to this, then A minus lambda I, what is that? That is equals to minus lambda 1 minus 1 minus lambda, right? Then determinant of A minus lambda I, that is equals to lambda square plus 1. Then this is the characteristics polynomial. Okay, characteristic polynomial. Then this lambda square plus 1 0 does not have any eigenvalue. Okay, does not have any eigenvalue in R, sorry, over R. So here is no questions of the diagonalizability then. Therefore no questions of diagonalizability here. Therefore no questions of diagonalizability over R. This field is very important because this only eigenvalue is the here lambda, I mean lambda square plus 1 equals to 0 only when lambda equals to square root of minus 1. Okay, so that is complex number, so there here is no eigenvalue over R. Okay, so in that case there is not possible to diagonalizable over R. But whenever, note that this is 2 by 2 matrix, but okay, if we consider A is equals to 0 minus 1 minus 1 0 0 0 0 0 and here is 2, then characteristics polynomial of A is x minus 2, or I can write it in lambda minus 2 lambda square plus 1 equals to 0. Then only eigenvalue of A is only eigenvalue of A over R, this is very important, is 2, because other two eigenvalue is the square root of minus 1 and plus minus square root of minus 1, but these two are not in real number, so therefore it is not, therefore it is also not diagonalizable over R. It is also not diagonalizable over R. So here A is in the 3 by A is of order 3 matrix and A has only one eigenvalue over R. Okay, now let's consider the pictures. Let A is a matrix such that and Px be the characteristics polynomial of A. Okay, then degree of Px is equals to 3. So then by fundamental theorem of algebra, that says that an odd degree polynomial must have a real eigenvalue. Then by odd degree polynomial over R, then as it is known that then by fundamental theorem of algebra, it is known that an odd degree polynomial over R, odd degree polynomial over R must have an real eigenvalue. Okay, must have a real solution, real root. And also, if alpha is equals to, if lambda equals to alpha plus I beta belongs to complex number where alpha beta are real and beta is equals to not equals to 0, be a root of a polynomial of degree polynomial over R, I mean real polynomial over R, then lambda bar, that is equals to alpha minus I beta, must be a root of that polynomial. Over R is okay. That means this is what I just want to say, that the polynomial with the entries from the real number. So that is a polynomial with real coefficient must have roots in pair alpha plus I beta and alpha minus I beta when beta equals to not equals to 0. So this is not something I just, but this is what I just want to say, but this statement must be written correctly. But main point is this. Okay, so now if we consider an odd degree polynomial, that is 3 degree polynomial, so one root is, so for a 3 degree polynomial, if for a 3, so in particular for a 3 degree polynomial, if there is a polynomial with real coefficient, if it has distinct real eigenvalue, then it must have all the 3 distinct real eigenvalue. So therefore, in that case matrix is diagonalizable. So main point here it is, let's consider P is a 3 degree polynomial, that is the characteristics polynomial of a matrix A, and as A is with entries from the real, then the characteristics polynomial will also have entries from real. Now for example, if it has distinct eigenvalue, that means it must have 2 real eigenvalue, distinct real eigenvalue, that means it must have 2 distinct real eigenvalue. But for a 3 degree polynomial, we know, or for a polynomial with real entries, if we have a if we have a complex number, complex root, so in that case the other eigenvalue will be in that case another eigenvalue will exist, and that will be the conjugate of that complex number. But here we have two distinct real eigenvalue, for example lambda and lambda 2, and they are real. So in that case there must exist other eigenvalue, because that is real polynomial. So for example, if we have x minus lambda 1 is a factor, x minus lambda 2 is a factor, then other factor will be x minus lambda 3, and this lambda 3 must be real, because otherwise if this is complex, then we should have another complex root of lambda 3 bar, right? But lambda 1 lambda 2 are real, so they will not be lambda 3 bar. So therefore there is lambda 3 bar must be real. Lambda 3 bar can't be complex number, I mean non-trivial complex number, because non-trivial means when b is equals to 0. For complex number b is equals to 0. So if lambda 3 is a non-trivial complex number, so there must exist lambda 3 bar, but lambda 3 bar must be lambda and lambda 2, but lambda and lambda 2 are real. So therefore we should have all the eigenvalues, we should have 3 eigenvalues and all of them are real. That is my point. So therefore according to that option B is correct. Okay, so let's go to another problem, and okay, I will try to do it quickly. So this is the problem. What is the let A be a real symmetric matrix? Which of the following statement is or are correct? Yet a real symmetric matrix. Okay, for a real symmetric matrix, A does not have a zero eigenvalue, that is false. Option A is not true. Why? Let's take A is equals to 0 0 0 0 is a real symmetric matrix, and have eigenvalue 0 as an eigenvalue, and 0 is an eigenvalue. Actually here it is only eigenvalue, but that doesn't matter. This is not correct. If A inverse exists, then A inverse is also real symmetric. Okay, let's do. Option B is correct. Option B is correct. Why option B is correct? So if A inverse exists, then A inverse A is equals to identity is equals to A inverse. Take transpose on both sides, then what will get? A transpose A inverse transpose is equals to identity is equals to A inverse transpose A transpose. Taking transpose on both sides, taking transpose on both sides, and it is known that I am just writing known that A B transpose is equals to B transpose A transpose, and as A transpose equals to A, as A is symmetric, as A is real symmetric, then A transpose is equals to A. Therefore A inverse transpose is equals to identity A inverse transpose is A. Therefore A inverse transpose is the inverse of A, as inverse of a matrix is unique, as inverse of a matrix is unique when it exists, okay. So in that case A inverse transpose is equals to A inverse, that implies A inverse is also real symmetric. Okay, this is symmetric is okay. Why it will be real? So let's recall what is A inverse. A inverse is equals to adjoint of A by determinant of A, but determinant of A will be real because all the entries are real, so determinant of A will be real. So this gives A is real. So this gives is real, because determinant of A will be real because all the entries are real, and adjoint of A, that is actually a matrix with cofactor. Okay, so cofactor are actually in that case also that will be real. Okay, so option B is correct. So A has at least one positive eigenvalue. That is not necessarily true. Option C is not necessarily true. C is not true. So let's take A is equals to -1 0 0 -1. Does not, it is real symmetric. It is real symmetric and does not have any positive eigenvalue. Okay, that is at least one positive eigenvalue, that is false. All eigenvalues of A are real, that is also false. Option D is sorry, all eigenvalues are really correct, that is correct, that is, this is correct. Yeah, this is symmetric matrix, so this is correct, this is correct. Option D correct. Why it is? Let lambda be an eigenvalue of a real symmetric matrix, A, then Ax is equals to lambda x for some x belongs to x is equals to some column vector. Okay, x n, this is transpose, belongs to R n cross 1. So in that case, x transpose A transpose is equals to or x conjugate, not transpose, x star A star is equals to lambda over x star. Here x star is equals to x1 bar xn bar. Okay, but that is again okay. So here need not be, vector need not be a real number. Okay, why vector need not be real number? Okay, so then let lambda belongs to C, lambda belongs to C be an eigenvalue of a real symmetric matrix A. So in that case, as A is real matrix and that is symmetric, then A transpose is equals to A. So that says therefore x transpose A is equals to lambda bar x transpose, right? So now x transpose A x is equals to lambda bar x transpose x. Okay, that implies x transpose lambda x is equals to lambda bar x transpose x. That implies lambda x transpose x is equals to lambda bar x transpose x. For some this is not 0. Okay, as this is not, as x is not 0 vector, that implies x star x is also not 0. That implies lambda equals to lambda bar. Therefore all the eigenvalues of a real symmetric matrix, therefore all the eigenvalues of a real symmetric matrix is real. This is an interesting result. Okay, I'm just making it. Okay, So now I'll do one more problem and stop today for today. This is 7. What it says, okay, so this is says let px be the this matrix, which of the following is or are correct. Px has eigenvalue 0 for some x. Okay, so let's take px is equals to, what is this, a plus 1 plus x square, 7, 1, 3x, 2x, 4, 8x, 7, 3. So therefore determinant of px is equals to 1 plus x square, 6x minus 28 minus 7, 21x minus 16x square plus 21x minus 16x square. I think I have made a mistake. 7, okay, this is, there is the problem. So this will be 9x minus 32x. 9, not 9x. Hmm, 9x. Okay, I made a mistake here. 1 plus x square plus 6x minus 28 minus 7, 9x minus 32x plus 1, 21x minus 16x square. Okay, so therefore this will be 6x plus 6x cube minus 21 minus 21x square minus, here will be 32, this will be 20 minus 21, so plus 7 into 21, 7, 1, 4 x plus 21x minus 16x square. So therefore it will be 6x cube minus 6x cube done, minus 20x square minus 16x square. I think this will be 44, yeah, 44 x square, yeah, 44 x square, and next will be 21, 29, oh god, this will be 3, 153 plus 21, 174 x minus 21. Please check it. Okay, so main point is that px, determinant of px is an polynomial of degree 3. Therefore determinant of px is equals to 0 must have a root. 0 must have a real solution, right? Solution x is equals to lambda. So therefore, so for that fixed solution, for that real solution x is equals to lambda, p lambda is not invertible and 0 is eigenvalue of the matrix p lambda. Okay, so what are the options here? First of all, p has a eigenvalue 0 for some x belongs to R. That's true for some x belongs to R. Second is that px, so therefore option A is correct. So here, from here one can say that therefore option A is correct. The second is that px has eigenvalue 0 for all x belongs to R, but that is not true, because as determinant of px equals to 0, and then as determinant of px is a polynomial of degree 3, then it can have maximum 3 distinct real root. So therefore for maximum 3 values, therefore for maximum 3 real number, maximum 3 real number x, px will have 0 as an eigenvalue, because for all other than that 3 real root, for other than that possible 3 real root, determinant of px is not equal to 0, and consequently 0 is not an eigenvalue. So therefore what we are getting here is that px has eigenvalue 0 for all x, that is false. Next, 0 is not an eigenvalue for px for any x, that is also false, because option A and option C is correct. Why this is correct? Because this is px is a 3-degree polynomial, so it must have a real solution. So there must exist an x for which determinant 0 is not an eigenvalue of px for any x. So there must exist a real number x for which determinant of px is 0. That means for that particular x, the matrix ps has 0 eigenvalue, 0 for some x. Okay, so that is also false. Now px is invertible for every x, that is also false. Why this is false? Because px is not invertible for at least one real number. So that is also option C correct, and option D is false. Main point is that as there exists a real number x for which determinant of px is 0, okay, that is because the determinant of px is a degree 3 polynomial, so there must exist a real number, there must be a real solution, okay, by fundamental theorem of algebra. So therefore there must exist an x for which determinant of the px matrix has eigenvalue 0, and secondly that is that px is invertible for every x, that is also becoming void, that is also cancelling out, and third is that 0 is not an eigenvalue of px for any x, that is also cancelling out. But as the determinant of px is of degree 3 polynomial, so px can have 3 different values of x for which 0 can be an eigenvalue, but not for all x belongs to R. So therefore third option is also not correct. Okay, so there we will stop here today, and I just want to make sure that the next class is on not on Saturday, but that will be on 4th March. Actually this next class is supposed to be on 1st March, but next class is on 4th March, okay, from 6 to 8 p.m. I will just write and stop here. Please join everyone, and if you have any doubt, please write to me. The mail ID ma21d018@smail.iitm.ac.in. Okay, so we are stopping here for today.